So we're into section 5.2 now. So these are all logarithmic integrations, but it basically is just substitution, except that we have a new formula that we can use. But you just have to be careful. Sometimes you may think it's logarithmic, involves logarithms, but it doesn't. So let's look here. We have problem number 4, which is the first one. So we have the integral of 1 over x minus 5 times dx. And we need something like 1 over x dx or 1 over u du. So this doesn't quite fit, even though you probably know what the answer is. It's going to be the natural log of the absolute value of x minus 5, but because anytime this is positive and 1, you can just take the denominator and you're in good shape. But let's not get ahead of the things. So we're going to let the whole denominator equal u. So du is just dx, because that goes to 0, and the derivative of x is 1, so you take 1 times dx, you get dx. Okay, so that's step 1. Step 2, calculate du. Well, we have dx directly, so we don't have to do anything else to that. Step 3 is substitute, so we get 1 over u du. So now we have it in a form that we know the integral. And the integral of that is just the natural log of the absolute value of u plus c. And then step 5 is to substitute back in. Well, u is x minus 5. So we just end up with the natural log of the absolute value of x minus 5 plus c. Problem number 8. We have the integral of x squared over 3 minus x cubed dx. Now the denominator is not raised to any power, it's just by itself. We have x cubed, but we'd have to have 3 minus x, the quantity cubed, to be able to do something other than the logarithm. So we would, step 1, which is choose u, just the whole denominator. Step 2 is calculate du. So you get negative from the negative sign. You get 2x from the derivative of x squared, and we multiply it by dx. Step 3 is to look up here and see if we have, actually step 3, we have x squared dx. So did I write something down wrong? Oh, this is x cubed, not x squared. I didn't realize that when I got to there, and it didn't match up. So let's try this again. So we're going to get negative 3x squared. So we have x squared dx, so if we solve for x squared dx, from here we get du divided by negative 3. Substitute into the original equation. So x squared dx is equal to du divided by negative 3. We have 1 over that, 1 over u. So let's factor out the 3 in the denominator and the negative 3 in the denominator. So we're left negative 1/3 times du over u. Now we integrate it with respect to u. So we get negative 1/3, this thing, times the natural log of the absolute value of u plus c. And the final step is to substitute u back in. So we get negative 1/3 the natural log of the absolute value of 3 minus x cubed plus c. Okay, that looks right. Next problem is 13. So this is slightly differently, because if you look at this rational function, the numerator is of higher order than the denominator. So you see that we can't just pick x plus 1 as being u, because the derivative of x plus 1 is just dx. And so we've got all this other stuff. So in this case, whenever you have this higher order, meaning this is squared and this is to the first power, you have to use long division to, or you could, in this case, you could use synthetic division because of the fact that it's just divided by x plus 1, but if it had been x squared or if it had been 2x. Synthetic division would not be so easy. So anyway, here we're doing long division. So you say, what do I need to multiply x by, my largest term here, to get x squared? Well, the answer would be x. So you take x times x is x squared. X times 1 is 1. And then we subtract these to eliminate this term. So x squared minus x squared is 0. 3x minus x is negative 4x. Okay, so then we bring down the term, next term. We say, okay, what number do I need to multiply x by? What do I need to multiply x by to get negative 4x? Well, the answer is negative 4. So negative 4 times x is negative 4x. Negative 4 times 1 is negative 4. I subtract this. So a negative times a negative is a positive. Positive plus the same is 0. This part is 0. And then we have 1. We have negative times positive is positive. So this would end up with 5. So this is our remainder. So this original integral becomes x minus 4, which is this thing up here, plus the remainder divided by the original denominator. So these are equivalent expressions, this and that. So now all we have to do is we can just integrate this. So the integral, first integral is going to be x squared divided by 2 when we integrate x. The second term is going to be 4x. The integral of a constant is the constant times x. And the last term is going to be 5, which is our constant. And then the integral of 1 over x plus 1, we just done these two, and all it is the absolute value of x plus 1. And then we add our arbitrary constant c. So that's the final answer. That's the integral. So again, we do the long division, find these two numbers, and then we take the remainder, divide by the original denominator. We end up with this expression, and we integrate each term separately. The first two are just polynomials. The last one involves the natural log. Number 19. Okay, so we have the natural log of x, quantity squared divided by x times dx. So this looks like you can think it's going to be a integral that results in the natural log because we have 1 over x, but then you've got this natural log term at the top. So this is actually a u substitution, but we're going to use the derivative of the natural log is 1 over x. So instead of u being x, we're going to let u equal the natural log of x. So when we calculate du, we will get 1 over x times dx. So the derivative of the natural log is 1 over x dx. And we look up here, and we have dx divided by x is du, so we can make that, and we can put in u for that. So this actually becomes, we end up integrating a polynomial. We get u squared times du. U squared dx over x is du. So we integrate with respect to u, and we get u cubed over 3 plus c. And then the fifth step is you just substitute in u again, back in. And so we get the natural log of x, quantity cubed, divided by 3 plus c. And you say, well, do we need to put the absolute value or something there? Because we always seem to be putting the absolute value, but in this case, no, because the original function had a limited domain. X could not be 0 because that would go, you'd actually have the natural log of 0, which is negative infinity over 0, which is who knows what it is. And any negative number, the function is not defined. So the integral is only defined also for the same case. So we have this trigonometric integral. So it turns out that sometimes trigs trig integrals can be represented. Ultimately, integrals involving trig sometimes can end up being the result in a natural logarithm. We've already done that when we derived the integral of the tangent, the cotangent, secant, cosecant. This is just a slightly different variation. So again, if we chose u to be the cosine of t, the derivative would be the negative of the sine, but we don't have negative of the sine. We have 1 over sine t. So the other choice here for u would be the denominator. So when we calculate du associated with this being u, you get the cosine of t. Derivative of 1 is 0. Derivative of the sine is cosine of t. And you multiply by dt. We see we have cosine of t dt. So we can just directly substitute into the original integral. We have du over u. So this is even though the original function involves sines, the actual integration involves 1 over u, du. So the integral is the natural log of the absolute value of u plus c. And then our final step is to plug it back in. So we plug u back in and we get the natural log of the absolute value of 1 plus the sine of t plus c. And that's your answer for the integral. Okay, we're on 48. And 48 is just a definite integral. So it's the same as we've been doing, except, of course, we don't have to substitute u back in because we're going to redefine the limits in terms of u. So we get 1 over x plus 2 dx between negative 1 and positive 1. So u is equal to x plus 2, du is equal to dx when x equals negative 1, u is equal to negative 1 plus 2, which is going to be positive 1. When x is equal to 1, u is equal to 1 plus 2, which is equal to 3. So we can rewrite the original integral first by changing the limits from negative 1 to positive 1 by changing them from 1 to 3. And then we have 1 over u du for the integral. So the integral of 1 over u du is just the natural log of the absolute value of u. We don't have to include c because when you take a definite integral, they cancel out. So we go from u equals 1 to u equals 3. So the final answer is going to be the natural log of the absolute value of 3 minus the natural log of the absolute value of 1. And the natural log of 1 is 0. So you just end up with the answer is the natural log of 3 is the integral, or the area underneath the curve. Our last problem is 4053. It's another definite integral. It involves trigs. It involves trig functions. So we're going to have the integral from 1 to 2 of 1 minus cosine of theta divided by theta minus the sine of theta, d theta. Okay, well, again, if we have a rational function like this, and unless the derivative of this is that, well, yeah, that's what happens in this case. But typically, if you have a rational function, you're not going to be picking the numerator to be the u value. It's usually the denominator, no matter what's going on. Okay, so what do we do? Well, step number 1, u equals theta minus the sine of theta. And so if we take the derivative of theta is 1 with respect to theta, just like x. The derivative of x is 1. The second one is minus the cosine of theta. The derivative of the sine of theta is the cosine of theta. So we go, oh, I forgot my d theta part here. D theta. Okay, so we have 1 minus cosine theta d theta. we have to redefine the limits. So let's call that 3. So when theta equals 1, u equals 1 minus the sine of 1. Whatever that is. Let's put the numbers in and just calculate it. And that's sine of 1, that's 1 radian. 1 minus, let's make sure the mode's right. Yep. 1 minus the sine of 1, which is equal to 0.15853. And when theta equals 2, u is equal to 2 minus the sine of 2 radians. So you get 2 minus the sine of 2 radians, and that comes out to be 1.0907. So those are my u limits. So I could rewrite the original expression. Instead of the integral from 1 to 2, it's the integral from 0.15853 to 1.0907. And the numerator is du, the denominator is u. So we integrate that, we get the natural log of the absolute value of u evaluated between 0.15853 and 1.0907. So that's the natural log of 1.0907 minus the natural log of the absolute value of 0.15853. So let's put that in, natural log of 1.0907 minus the natural log of 0.15853, and I get 1.9286. Okay, I'm going to take the answer in this case. Okay, so that's correct. Everything's good. So, kind of a review here. There's really nothing special going on here. It's just some functions, when you integrate them, you can rewrite them as du over u, and u substitution works exactly the same. Substituting the limits in terms of u instead of in terms of theta or x, you just do the same thing you normally do. So there's nothing really new and exciting there.